Our book is a little different to other books. Usually books about like competing models for the Big Bang, they're usually written by one scientist who has one model and they're trying to sell you their model of the Big Bang. And what we wanted to do was something quite different, which was let's survey the models. Niayesh has come up with several of them, but obviously there's many others. So I went and interviewed all of the leading cosmologists who have come up with the others, including, a lot of the big names in the field, Stephen Hawking, Roger Penrose, Alan Guth. These are like the biggest names in cosmology, and I went to interview all of them. So we get a sort of exchange of ideas, sometimes pleasant and sometimes a bit more feisty, but that's kind of the idea of the book. That's why it's the battle of the Big Bang.
Right, and you have a YouTube channel, and I'll put a link to your YouTube page
Yeah,
on in the show notes so people can easily find it. But you do interview experts in science and philosophy with a focus on cosmology, and
that's
it's
right.
a fascinating channel that for anybody who wants to wander into these esoteric subjects. Now, what's the problem with the Big Bang model? It seems like it's pretty simple. There's a Big Bang, the universe happened, and end of story. What's the problem?
Well, there's loads of problems actually, but maybe we'll dive straight into the biggest problem, which is that the standard Big Bang model uses Einstein's theory of general relativity, and this is an extremely well-tested theory. Been tested to, I don't know, at least probably a dozen decimal places. So there's no doubt this theory is correct, but it's correct within a particular realm, shall we say, a domain of applicability, I think is the phrase we would use in physics. So um, when we get to the very extreme conditions of the Big Bang, what most physicists think is that this theory doesn't take into account the other sort of cornerstone of modern physics, which is quantum mechanics. So quantum mechanics, if you like, is the physics of the very small. General relativity is the physics of the very big. So for very big stuff, we can use general relativity. Very small stuff, we can use quantum mechanics. And the fact that the two actually contradict each other is not really a problem. But at the Big Bang, then it is a problem because both of these theories are likely to be relevant. So what physicists hope is that they can come up with a new theory, a theory that incorporates quantum mechanics and general relativity. This would be called a quantum theory of gravity. Um, so the Big Bang was first proposed, let's say, back in the 1920s, and it's been developed over decades. And in the 1960s, something very important happened. A number of very important things happened, but for our particular topic here, um, Roger Penrose and Stephen Hawking proved these theorems that said that the curvature, the temperature, the pressure, everything would go to infinity at the Big Bang, and that's not taken well by physicists. Um, so the problem is, oh well, maybe we're using the wrong theory. We're using Einstein's theory of general relativity, so maybe we can't trust this Big Bang singularity. Maybe it should be replaced by a quantum theory, and that's probably the biggest issue that we tackle in the book. But there are others as well. There's actually many problems with the Big Bang that we go over.
Right. And so your hope is to give people a broad overview. And after reading the book, you really do give a broad overview of all the different competing theories. And that is the battle. And there's the question of what happened. Of course, everybody wants to know what happened before the Big Bang. And
That's right.
uh, these are seemingly like if you want to wander into some territory that seems like a question you can never find the answer to, that seems like a prime candidate of something. And yet we wander into that territory in your book, The Battle of the Big Bang. So tell us a little bit about what does any, you kind of, a little spoiler alert, you don't really endorse any one theory over any other. There's not one clear winner. And but as far as any answer, to me, the most elegant one is that maybe the universe always existed. There was no before, you know. What do you
Yeah, and
think?
then many models that we examine have that property that the universe has always been there. And some people might find that very surprising because they might think, well, we all know that the universe was born at the Big Bang, that 13.8 billion years ago, time stopped ticking. And that was the beginning of time. So asking what came before is just a totally meaningless question. There can't be any before if time started at the Big Bang. But that relies on these Penrose-Hawking theorems that, as I said, many physicists would question and say, well, you're using general relativity beyond its domain of applicability. So, of course, you're getting this nonsensical answer of infinite density, pressure, temperature, curvature. So, if we use a quantum theory, and in fact, Roger Penrose and Stephen Hawking themselves have sort of suggested that we shouldn't trust this singularity. That maybe the Big Bang singularity was not the beginning after all. Penrose, in particular, very strong on suggesting that the universe is eternal in both directions of time, into the past and the future. Hawking was more sympathetic to the idea that the universe did have a beginning, but it's a very strange beginning in the way that he thinks of it, and it's actually debatable whether his sort of modified version of the Big Bang actually has a beginning or not. He thought it did, but I'm not sure quite of his colleagues thought it did. So, so I think it's certainly possible that the universe has always existed. It's possible that it had a beginning. It might be a beginning at the Big Bang, or it could be a beginning earlier than the Big Bang. But
Why was his theory so strange? You characterized Stephen
oh, okay,
Hawking's.
yeah, yeah. So Hawking, was obviously the co-author on the Penrose-Hawking theorem that proved that the universe had a beginning at the Big Bang. But Hawking was very quick to suggest that we shouldn't trust this conclusion. He said, absolutely, we haven't included quantum effects. And when we do, maybe the picture is going to be very, very different. So actually, there's a lesson here because if you look at black holes sort of swallow everything up and they swallow information, which actually turns out to violate thermodynamics. So it seemed very strange and hard to believe. But and then a scientist called Jacob Bekenstein said, no, black holes must obey the laws of thermodynamics. And Hawking was like, but they can't because if they did, they would radiate, they would give off heat, and nothing can escape a black hole. And so there was this fight between Hawking and Bekenstein about black hole thermodynamics. And the person that proved Bekenstein right was Hawking himself. He decided, well, hang on, let's apply quantum principles because I've only looked at general relativity, this theory of the big. Let's look at the theory of the small, quantum mechanics. And when he did that, he showed that actually black holes do radiate, and so they obey the laws of thermodynamics. And now it's very well established. There's a formula for calculating the temperature of black holes and the entropy of black holes, and the entropy one is called the Hawking-Bekenstein formula. So Hawking thought, well, okay, I've done this quantum modification to black holes. Let's do the same for the Big Bang. So he tried a sort of quantum modification to his singularity theorem. This was in collaboration with a scientist called James Hartle. So they came up with something called the Hartle-Hawking model. And what this suggests is that as we go back to the Big Bang, instead of having 3 space dimensions and 1 time dimension, which is the world around us that we know from our everyday world of experience, actually what happens is the time dimension transforms into a space direction. So you don't have 3 dimensions of space and 1 dimension of time. You have no dimensions of time, but 4 dimensions of space. So you have this sort of strange quantum world where there's no time. Now, is that a beginning? Now, Hawking did interpret that as a beginning, but if we were to draw it out, like as a picture, think of the Big Bang singularity as like a cone with a sort of sharp edge point at the beginning. Whereas this picture would look more like the bottom of a shuttlecock, so it would have a sort of smooth surface. Now, in which case, it doesn't necessarily go on forever, but on the other hand, there's no point that you could pick out as the beginning because all points are as good as any other on this smooth surface. There's another sort of thing that they introduce, which is something called imaginary time. And people that know mathematics might be familiar with imaginary numbers, but for those that don't, maybe I can sort of briefly explain what we're talking about here. So if you can take the number 9. If I ask you, what's the square root of 9?
3.
You can guess. Right, 3. But it's also, do you know, there's another number that's a solution to that equation?
It would be -3.
Correct, yeah. So +3 times plus 3 gives you 9. Minus 3 times minus 3 also gives you 9. But
Hmm.
what if I asked you, what's the square root of minus 1? Or any negative number? There's no number that's no conventional number that multiplied by itself will give you a negative number.
Hence,
But
imaginary.
so mathematicians use this trick called an imaginary numbers, where they do square to negative numbers. But weirdly, these imaginary numbers will turn up in quantum mechanics. So the idea also would be that there's sort of an imaginary time. Now, when we say imaginary here, we're not meaning like, it's like sci-fi, fictitious, anything like that. We mean in the sense of imaginary numbers. So now, if you trace the universe back in imaginary time, you get to this sort of what they call the no boundary state. But you could also ask, well, what happens in real time? And there, actually, it's been argued that the no boundary state is infinite into the past. Now, there's controversy about this. Um, so, how to interpret the no boundary proposal, whether it's a universe with a beginning or not, is up for debate. But that's the basic picture that they came up with, and that's one of many proposals for transforming the Big Bang into something more intelligible.
Phil, this also makes me remember of another thing that you talked about in your book, which is you're talking about Stephen Hawking applying quantum mechanics theory to the very big or the beginning of time, black holes as well, the Big Bang
Yeah.
itself. But people have taken another well proven theory, which is the theory of natural selection, Charles
Mm,
Darwin, and
right.
applied it to the multiverse or the universes, that perhaps we are just
Yeah.
one of thousands, millions, billions, trillions, or more universes out there, and we have just outcompeted the other universes out there, and ours is just top of the heap, or at least one of the surviving species of universes out there, whereas a bunch of other universes failed because their laws of physics were just not as tightly tuned as ours to produce something interesting that we call life.
That's right. I mean, there are, well, maybe we could sort of separate the two ideas of multiverse and cosmological natural selection. So, first off, there are many different ideas that could generate multiple universes. They could be in time, like in a cyclic universe. It could be in space, like in what's called an inflationary multiverse. Maybe I'll just sort of unpack the inflationary multiverse. So, there's a theory called inflation, and this is actually the dominant view of cosmologists, I would say. Although, having said that, we did interview black hole physicists, and it was the most popular choice for a theory of the early universe, but it didn't actually get majority support. So if you rank them all, this would be number one most popular theory, but it got just shy of 50% support. But that was black hole physicists. I suspect if you survey cosmologists, it would be the majority view. And it's in textbooks. This is not like some wacky, crazy idea that few take seriously. I mean, this is standard cosmology, and that is in the very early universe. There was a period of exponentially rapid expansion called inflation, and what inflation does, though, is that it cools the universe down to sort of zero, almost zero temperature, and then when this exponential expansion ends, all the energy that was in the inflating space gets converted into sort of matter and radiation. It is the Big Bang. The Big Bang is what happens when inflation ends. Um, but so it creates a sort of what they call a pocket universe. But the idea is it wouldn't only create one pocket universe, it would create an infinite number of them. And in the book, we go into what the mechanism is, but we don't really need to worry too much about that. So it creates an infinite number of universes. Now, this has been used to solve a puzzle in physics. Now, this puzzle is somewhat controversial because not everyone agrees that it is a puzzle. But for those that think that it is a puzzle, they say that, well, if we look at the constants of nature, the mass of the electron, the speed of light, things like this, they all have values which seem to be very life conducive. That if you change them a little bit, you wouldn't get a life emitting universe. So the question is, well, how did we get so lucky? Now, some people say this is a pseudo problem, that you can't really say that these values are unlikely because you don't really have a theory of what chose the values, so it's not a problem that we should even think about. But others take it seriously and they say, no, we need a solution to this. So one solution is basically think of a lottery. If you want to know what's the odds of winning the lottery, very, very low. So now you find out that someone won the lottery, and you want to know, how is that possible? How could someone have won the lottery? It's so incredibly unlikely. Well, the simple solution is that, well, there were lots of lottery tickets sold. And if there are lots of lottery tickets sold, then it's no surprise that somebody won. But there's a twist here, because in the cosmological setting, you have to observe a winning lottery ticket. You couldn't observe anything else. Whereas for a lottery, you don't have. It could be that nobody wins, right? That happens quite frequently, that nobody wins a lottery. But here, you couldn't be in the position to observe a world where you didn't win the lottery, in the sense that here I'm using that as a metaphor for having the right values for the constant of nature. So a multiverse would seem to solve this, what's called the fine-tuning problem, or anthropic coincidences, they're also called. So that's one solution, that we got lucky because there are just so many universes with all different values for the constant of nature, and one of them had to have life-emitting values. And of course, we have to be in that one. So that's one solution. But there's another solution. So if we think of this problem in the setting of biology, we could make the same analogy, and we could say, look, if you just randomly selected genetic material, threw it together, you're extremely unlikely to get a functional organism. So what's the answer? Well, the answer is they weren't thrown together randomly. There was some selection process. And in biology, that process is natural selection. Basically, if you have any slight advantage over your competitors, then you get to pass your genes on, and they increase in the gene pool. So there's a Darwinian process that is not entirely random. So it may be the mutations are random, but what selects the positive mutations is definitely not random. So here, if we want to have an analogy in cosmology, we need some mechanism for the universe to reproduce itself. And Lee Smolin and others have suggested that black holes actually might give birth to new universes, and there are sort of very interesting physical proposals to how this might actually work. So if that's true, then the parent universes have children. And now, by conjecture, well, we could imagine that the constant of nature change very slightly from one to the other. And then those that make more black holes, because it's black holes that are generating the universes, they will give rise to more universes. And so the constants will be selected for making black holes. They're not selected for life. Life's just a happy byproduct because, well, to make black holes, you want stars, and stars give birth to life. So when we say it's fine-tuned for life, we're not really saying it's fine-tuned for life. We're really saying it's fine-tuned for stars, or complexity maybe more generally. So this would be an alternative mechanism to the one. It's different to the lottery case, because the lottery case, you just have lots and lots of lottery tickets, and one of them will win. But you have to be in the winning universe. So that's called anthropic selection. Right. So it's sort of a statistical selection effect. But here we're using natural selection. So that's kind of quite a different idea, although what they have in common is that they both say there is lots of universes. So in some sense they have a lot in common, but in another sense they're very different. And in fact, one of the key differences is in the natural selection, you might expect to be in a more typical universe because there'll be more of these. Whereas for the other case, the sort of multiverse lottery ticket case, you might be very rare in the whole sort of ensemble of universes. It might be very few life-emitting universes. But hey, there only needs to be one, so that's enough.
That is enough for us. That brings up. You said many things, Phil, and remind people, if you guys want to dive much deeper into all this, you got to buy his book, which just came out.
I hold it up.
There you go. Thank you. Yes, the Battle of the Big Bang is the book.
Yeah.
And it's a fantastic overview of all these details and much more. I do want to go into a few of the theories in rapid fire. That I think are fascinating and things that I had never heard about. One of them, like this idea that maybe we're in a white hole. Other people say that we're in a black hole. That briefly touch on that.
Well, so black holes. So actually, interestingly, the Penrose-Hawking theorems that we talked about before, they were first created by Penrose, and he was just looking at black holes, and he said there must be a singularity in the center in a black hole. And then what Hawking did was say, I'm going to take your theorem and apply it to the Big Bang, and I'm going to prove that there's a singularity of the Big Bang. Now, if the singularity is going to get resolved, then it should get resolved probably both in a black hole and in a big and at the Big Bang. So people have suggested, well, maybe these two things are kind of the same thing. So it could be that black holes give birth to new universes, and there are a number of mechanisms for that. But we could think of, if they do that, the black hole could reverse itself. So one idea put forward by, for example, Carlo Rovelli, who's worked on a theory called loop quantum gravity, which is a sort of rival to string theory. String theory is the most famous attempt to do quantum gravity and trying to put these two theories of physics together. And what Rovelli and his collaborator Francesco Vidotto have suggested is that actually what you get these, well, actually this comes from loop quantum cosmology, trying to apply the theory of loop quantum gravity to cosmology. And what they think is that you get a maximum density, so it doesn't go infinitely dense, it becomes maximally dense. And just think of water being poured on a sponge. The sponge will absorb the water, but eventually the sponge won't absorb any more water, so it will actually start repelling water. So similarly, space can absorb more and more matter and energy as you compress it and compress it and compress it. But you get to this maximum point, and if you try and squeeze after that, it will just repel things. So in the universe setting, it would be a big bounce rather than a big bang. But in a black hole setting, the material would fly out of the black hole, and it would do so very, very quickly. But it's quickly from the point of view of someone falling into the black hole, but someone from outside, time slows down. So the stuff comes out. Now, if we think of a white hole is the absolute opposite of a black hole. So nothing can escape a black hole, and nothing can get into a white hole. But if you think about, so imagine everything getting repelled out. What does that look like? Well, that looks like the Big Bang, doesn't it? We're all in this thing. It's all sort of big. So you could say that the universe is a white hole almost by definition.
Right.
But there are differences between the sort of black hole singularity and the Big Bang singularity. So there are issues about how to marry them together, and there's various ideas. My co-author, Niayesh, has an intriguing one, which is that our universe came from a higher dimensional black hole. And there's reasons in conventional black hole physics to think that, you know, there is a sort of dimensional reduction. So when we think about black hole horizons. And so if ours was to come out of a black hole, then maybe it's a higher dimensional black hole. We need one more spatial dimension. So there's all kinds of ideas linking black holes to the Big Bang. And yeah, they're absolutely fascinating. Very, very intriguing, I think.
Let's talk about a couple of theories. One of them is the triple C, or maybe CCC, Conformal Cyclic Cosmology. You discussed that in your book, The Battle of the Big Bang. Give us a 2-minute overview of what triple C is.
Okay. Yeah. So CCC is the term that people use for it. It's a very controversial idea. In fact, I should say that a lot of the ideas are controversial. One of the reasons that we called the Battle of the Big Bang is because what we wanted to do in the book is to expose the sort of fights that go on between cosmologists. This is not just sort of dry working out equations. There's a lot of human passion, and no more controversy is going to be found than in CCC, because it's created by, you know, one of the absolute giants of cosmology, Roger Penrose, who won the Nobel Prize in physics. And what he suggested is that well, there's this thing called conformal invariance. So it sounds like a technical term, but don't be scared. It's actually pretty simple. Just think of a triangle, right? Add up the angles of a triangle. They add up to 180 degrees. Now double the size of the triangle. What do they add up to now? Well, still 180 degrees. So you might say that the angles of the triangle are conformally invariant. And in other words, they don't care about scale. And in fact, if there's no mass in the universe, the whole universe is conformally invariant. There's no scale. And what Roger suggests is that at the Big Bang, the temperatures are so hot you can't form mass, so there's no scale. And if you go forward in time enough, you know, maybe even an infinite number of years, then there won't be any mass there either. This is one of the controversial bits. And then the universe sort of forgets how big it is, and it can transform from this diffuse big universe into a hot, dense universe. And so the Big Bang at the beginning and the sort of cold, diffuse universe at the end can be linked, and we actually get a cyclic universe. But interestingly, it's not like the conventional cyclic universe. It doesn't expand, contract. Rather, it just expands. and then conformally transforms from one to the other. And that's Penrose. But it was so controversial because he suggested that he had empirical evidence for it. And a lot of other physicists said, we're not buying that. You're just not doing the statistics properly. So there was a huge fight as to whether there was evidence for this or not.
And it still rages on. Another huge fight is over the Ekpyrotic universe. What is that?
Right. So this was an attempt to use string theory.
Sorry, let me quote one part of your book. You said it's movement of the branes as in branes, is controlled by a spring-like force. Yeah. Now, of course, people hearing that, they're all already scratching their head, especially if they don't know what a brain-like state is. So if you can briefly just tease people, because again, I got to encourage people to dive into this, Battle of the Big Brain book itself. But Ekpyrotic universe, what's your nutshell summary?
All right. So basically, this was an attempt to use string theory to look at the Big Bang. So string theory is this attempt, the most famous one, I'm sure, because Sheldon in the TV show Big Bang Theory worked on string theory, and it's had lots of publicity, books and TV shows all about it. So this is seen as probably the best, the leading candidate to connect quantum gravity with general relativity. And what it says is that we replace point particles with extended objects called strings. But then it turned out, as the theory was developed, there were other objects. So they came up with these other things called branes. So think of a brane as like a sheet, maybe think of a bed sheet or something like that. And it turns out in the theory, these sheets, these membranes, branes is short for membranes. So think of these two membranes. They can't, basically a membrane in this theory cannot exist alone. It has to have at least one other. I mean, it could have many others, but it has to have at least one other. And then the suggestion was that, well, hang on, this would effectively embedded in one of these branes. So what would happen, the scientists wondered, if they collided? Well, if a brane collided, it turns out that there would be an enormous burst of matter and radiation. And they're like, oh, that sounds just like the Big Bang. So they worked out a model called the Ekpyrotic model. So Ekpyrotic means born of fire, and it comes from the ancient Stoic views. So ancient Greeks, they had this view that the universe was born from this sort of conflagration point of fire, cleansing of the universe through fire. So that's why it's called Ekpyrotic. So that was their view, and they tried to challenge the inflationary view that we mentioned before, and of course that led to another fight between the proponents of the Ekpyrotic model and the inflationary model. And that rages on, although the proponents of the Ekpyrotic model have they've actually done away with the current ones, the people who are still suggesting this theory is right. They've sort of done away with the picture of the colliding branes and tried to make a simplified version, which also is cyclic. But that's cyclic in the more conventional sense of expand, collapse, expand, collapse.
Right. In a couple of minutes that we have left, let's talk also about the Carroll-Chen model. And by the way, briefly, one of the things I love about your book is that these are very esoteric, hard to conceive of concepts. People are probably struggling to keep up with you already. One of the things I really like about your book is that you have a lot of illustrations, which to me speak 1,000 words, really. And it helps you kind of visualize these things. And you do have an image about the Carroll-Chen model. In your best 2 minutes, how could you sum up that model?
Right. So I guess it has two interesting properties. One is that I should say they're trying to solve this mystery as to why the entropy of the Big Bang was so. But entropy is, if you like, a measure of disorder. It's not precisely that, but roughly speaking, it's that. And they're trying to say, well, how did we get this low entropy start to the universe? So their idea, there's sort of two ideas that I think are interesting here. So one is that maybe there could be a mother universe to give birth to baby universes, and there could be regions of that baby universe that have low entropy, even though the mother universe, the entropy is growing. Right. But there could be small regions of low entropy, and they bud off. And that's how we get our low entropy beginning. It's not that we actually had this low entropy beginning sort of ex nihilo. It came from a mother universe that has always increasing entropy. Now, the other thing that's interesting about it is that when you look at the whole big picture, the arrow of time sort of reverses. So if we think of us going forwards in time, if we went back far enough, we might actually find that we go forward in time again. The way the analogy that we had is that time is like dualists as they pace away from each other before they turn around. They both think they're going forwards in time. Or they both think they're going forwards. From their perspective, they are going forwards. But this idea has this reversal of the arrow of time. So in one branch of the sort of multiverse, the time arrow is going one way, and if you go back enough, you'd find it flips and goes the other way. So this is a more general idea, and we call them the Janus universe, or that comes from an Oxford physicist called Julian Barber. And the idea is it's like the Roman god who had two faces looking in both directions of time.
Mind-blowing stuff, Phil. I really appreciate you taking the time to just tease us about your book. And again, this has probably raised 1,000 questions for people. Read the book, The Battle of the Big Bang, to learn more. It just came out today, and put in your order in there. And you're still going to have 1,000 questions even after you read the book, but maybe you only have 100, down from 1,000. But this is a never-ending battle. Thank you so much. Remind people how to find you and where they can subscribe to your YouTube channel.
Right, so just go on YouTube, just type in Phil Halper, Halper, and you'll find my channel. And also, if you like the cosmology stuff, you can go on playlists. And there's a cosmology playlist, because I do other stuff as well. But
I will put those down in the links below.
Brilliant. Thank you so much. It's been a pleasure being on.
Okay, thank you again. Excellent.